I wish you all, okay, now I wish you all very welcome to this second webinar of the LEAP webinar series, where we present and discuss results from the project Legacies of Agricultural Pollutants, which is funded by the EU Water JPI, or Joint Programming Initiative. And the title of today's webinar is Measures, Costs and Benefits from Nutrient Regulation. My name is Jerker Jarsjö. I'm a leader of the research group from Stockholm University, Department of Physical Geography. And we have three presenters today: Roy Brewer from the University of Waterloo, Canada; Brian Jacobson from the University of Copenhagen, Denmark; and Serene Wilson, also University of Copenhagen in Denmark. And maximum time for each presentation is 20 minutes. And then there is time for questions afterwards. And depending on time, we might also get the opportunity for concluding discussion in the very end. And to ask questions after the presentations, just raise your hand or write in the chat, and we will give you the word to ask the question. And it would be good also if you, before asking the question, would say your name and affiliation. So with this short summary, I would like to give the word to the first presenter today, Roy Brewer, who's going to talk about spatial heterogeneity in the Grand River watershed. Please go ahead, Roy.
Thank you, Jerker. Can you see my screen?
Yes.
Okay, let me just get rid of the, I just want to close this. Okay, so good morning, good afternoon. I'm going to talk about the work that we did in Ontario in the Grand River watershed in the project LEAP, where we developed a spatial economic optimization procedure for agri-environmental measures called best management practices here in Canada to reduce phosphorus losses that run into the Great Lakes. Here you see the names on the top of the team in Waterloo, and this was a true interdisciplinary collaboration between scholars from Waterloo and the Grand River Conservation Authority. We've got Louise Heiming with us here today as well. Mark Anderson, her colleague, helped us with the data, and we collaborated with Wang Hongyang and Yongbo Liu from the University of Guelph. So a little bit of background about the case study here. This is Lake Erie, one of the most polluted and lakes facing most of the pressure when it comes to runoff of phosphorus. We've got some major eutrophication challenges here, and they are coming along with a very high estimated economic cost of around 270 million Canadian dollars per year, an estimate that was made a couple of years ago, just for the Canadian side of Lake Erie. So these costs refer to the economic damage costs of eutrophication to all kinds of socioeconomic activities in and around Lake Erie. There have been new policy targets set already a number of years ago to reduce phosphorus loads into the central and western basins of Lake Erie by 40% compared to 2008 baseline loads. And although there isn't really a concrete policy target yet for the eastern basin, the Grand River watershed is expected to be a priority for future action because it's one of the largest contributors of phosphorus into the eastern basin, around 40%, and it's the largest watershed draining into Lake Erie on the Canadian side. So this is a land use map of the Lake Erie watershed, including the Grand River watershed. We are here in Waterloo, and here where this arrow is pointing at the bottom, where it says restriction, that's the mouth of the Grand River, where the water flows into Lake Erie. And so there is a Canada-Ontario Lake Erie Action Plan that targets the reduction of phosphorus loads into Lake Erie. The main objective of the work was then to identify how can we reach these reduction targets at the lowest economic costs possible. So that's what economists call a cost effectiveness analysis. And that is what we did. So we tried to identify which kind of best management practices should be implemented, but also where in the Grand River watershed that should be implemented. The watershed is around 6,800 square kilometers in size, so a pretty sized watershed, and there are different places with different pressures when it comes to runoff into the Grand and then draining into Lake Erie. We focus on crop production here, and the work is directly linked to a so-called to the Rural Water Quality Program that was implemented in Ontario to work with farmers to adopt best management practices on their land to reduce nutrient runoff into the Great Lakes. The novelty of the work is presented here. It's the first cost effectiveness analysis for the whole watershed. There have been some applications of the model SWOT in the Grand, but that was in a very small part of the watershed. You see that here in the second bullet point. And we're also doing a cost effectiveness analysis instead of just an effectiveness analysis, because there have been some previous work in the region of Waterloo showing, for example, in the context of groundwater leaching of nitrates, that the ranking of measures may change if you also include the costs of these measures. And very recently, a publication came out that showed that if you focus on relatively small areas, you may miss the bigger picture, and you may have a local optimum, but not a optimum for the entire watershed. What is also new is that we will work with the financial program implementation costs that were provided by the Grand River Conservation Authority, but we also made an estimation of the total economic costs associated with BMPs. We look at conventional measures and also these so-called nature-based approaches. We'll look at wetlands. And we account with the help of SWOT for upstream, downstream relationships, and I'll try to explain that in a second. So the starting point was a very big database that we were given by the Grand River Conservation Authority related to the implementation of the Rural Water Quality Program, 20 years of BMP data for more than 4,000 projects over the time period 1998 and 2017, focusing on measures in both crop and livestock farming. We only focus on the crop farming part. The cost data that was provided was made comparable over time by us. And then linked to the effect that these BMPs were expected to have on runoff and ultimately on the water in Lake Erie. This is an overview over time of the different projects, and this is a map showing you also the spatial distribution of where these projects were implemented over the last 20 years. And the darker the color, the more measures that were taken. So especially in the central western part, you see that the color is dark. So most of the measures were taken there. We then worked our way through the different measures, and a very important caution that I have to make here is that not all the measures that were included in the database related to the Rural Water Quality Program were the same as the kind of measures that we considered in the analysis that I'm presenting here. And this is the first one where we look at a reduction in fertilizer application. There is a nutrient management plan as a BMP that tries to address the 4 R's in Ontario: right source, right rate, right time, right place. We only focus on the rate. We only look at the application of fertilizer, the amount of fertilizer that is applied to land. We distinguish between 5 fertilizer reduction scenarios: 10, 20, 30, 40, and 50%. We looked at the cost of the nutrient management plans, but then we also considered the economic value of these fertilizer reduction scenarios. taking into account what the estimates are for nutrient application on land. You see that at the bottom on the left-hand side of this slide, how much nutrients, phosphorus and nitrogen is applied for different types of crops in different seasons of the year. And then we looked at the implication of reducing fertilizer on crop yields. And for that, we use nonlinear relationships that exist between fertilizer application and crop yields. And we looked at the opportunity costs. So what is the loss in economic value if these reduction scenarios are implemented? And this is an example of how this nonlinear relationship looks like when it comes to the application of fertilizer on a hectare of land and the crop yield. So we made use of this nonlinear relationship and related that to the opportunity costs of cropland in the Grand River watershed. Similarly, we looked at cover crops or after crops, where we try to assess what exactly is the economic value of planting cover crops. What we found out is that there are only a limited number of studies that evaluate the economic returns of cover crops, and there may be a potential loss in profits, but in some cases we also found studies where there actually are positive profit margins to cover crops, depending on the type of crop that is being used. We looked at the incentive payment in the Rural Water Quality Program, which means that farmers got an amount of money to incentivize them to grow cover crops. And we tried to find data on what the economic implications are. It was a very hard search. We managed to find some data from Ohio State University Extension Service there, and we assumed that there would be vegetables used as cover crops, and that actually resulted in a positive profit for the farmers using cover crops. Riparian buffer strips, we looked at the cost and effectiveness of these buffer strips as well, and there is a lot of discussion in the literature when it comes to how wide should these buffer strips be. So we used 4 scenarios here based on the literature that is cited here: 3 meters, 5 meters, 10 meters, and 30 meters width. And we only implemented these riparian buffer strips in places in the watershed where the slope was more than 5%. Again, we compared the cost sharing, which means that part of the costs were reimbursed to the farmers, and the incentive payment that farmers received for incentivizing them to create these buffer strips. And then we used again the economic value, the opportunity cost, if you take productive land out of production, to estimate the economic value. Because we had some guidelines on where these riparian buffer strips could be implemented, they were only implemented in part of the watershed, as you see here. And then finally, wetland restoration. We followed Liu et al. And so we made assumptions about how much cropland could be converted into wetlands, or how much wetlands could be restored on existing cropland, assuming 2% and 4%. And again, we compared the cost sharing and incentive payments from the Rural Water Quality Program with the economic value that we estimated. And in this case, compared to riparian buffer strips, we also added the average construction costs of wetlands based on a meta-analysis of the Canadian literature. So how costly is it to restore and create wetlands on cropland, and what are the opportunity costs involved? And the opportunity costs are again based on the loss of net operating income from cropland in Ontario. That's information that we got from Statistics Canada. So those were the different types of BMPs that we investigated, and then the methodology that we used to assess the least cost way of reaching these phosphorus reduction targets is presented here. There is a simulation part and there's an economic optimization part in the analysis. Starting on the left-hand side, the simulation, we used SWOT. I already mentioned the model SWOT before, where we are able to look at a specific BMP and how much phosphorus it reduces on the land and how that then impacts the water. So based on SWOT, we were able to assess by how much every BMP, depending on where it was taken in the watershed, would contribute to a reduction of the total phosphorus load going into Lake Erie. And then knowing the baseline situation, how much is currently flowing into Lake Erie, we impose these reduction targets, and then based on the information on the costs of these BMPs, we look for the least cost way to achieve that target. So very quickly about SWOT, this is not my field of expertise. Someone else ran the models for that. It's an open source model. It had already been developed for the Grand River watershed, but we calibrated and validated it over a long period of time, almost 30 years, where we converted the more than 1,000 hydrological response units in the 90 sub-basins that we identified in the watershed. And it was validated, calibrated on water flow, sediment loadings, and nutrient loadings. It worked well, to very well. So here are some results for the flow. Here are some results for the total phosphorus. So the results were acceptable in calibrating the SWOT model for the entire watershed. And then based on available data and information, we estimated how much the average loading is of total phosphorus entering Lake Erie every year over that time period of 27 years. So that's an estimated 386,000 kilograms. And then when we go to the optimization component here, we want to reduce that baseline load by 10, 20, 30, 40, or maybe even 50% based on this Canada, Ontario, Lake Erie action plan. So these are our policy scenarios. Yeah, so we know what comes out of the mouth of the river, draining into the lake, and we want to restrict that. And we use scenarios of 10, 20, 30, 40, and 50%. And then the analysis that I present you, the results that I'm going to present you now, identifies which BMPs should be implemented where to achieve these reduction percentages at the lowest cost possible. So I'm going to show you some results based on the ranking of BMPs, and then I make a comparison based on the effectiveness and the cost effectiveness of these measures. We also have an entire analysis on the spatial heterogeneity in cost effectiveness that I'm going to just glance over. I don't have time to show you all that. And then I'm going to present you the results for the least cost way to reduce phosphorus loading by these percentages. So let's start with the ranking. If you just look at the environmental effectiveness of the BMPs, and I've aggregated them here across nutrient management, so the reduction of phosphorus application on cropland, the use of cover crops, buffer strips, and wetlands. If we simply look at how effective they are in reducing the load, this is the ranking. Wetlands are the most effective in reducing total phosphorus in kilograms per hectare, followed by buffer strips, nutrient management, so the reduction of fertilizer, and then finally cover crops. So if you just look at the effectiveness, you don't look or you don't consider the costs, this would be the preferred order in which you would implement these BMPs. Then if we add in the costs and as well, and we make a distinction between financial implementation costs based on the Rural Water Quality Program and the estimated economic costs that I briefly showed you before, the ranking changes. It changes quite dramatically. So this is just on the effectiveness, and this is based on the cost effectiveness. And even if you make the comparison between the financial and economic costs, you see that there is no measure that has the same number. So the ranking of the measures changes if we account for the costs as well as the effectiveness, and the ranking changes again if we look at financial versus economic costs. Yeah, so wetlands were most effective, but they are not most cost effective, as you can see here in the ranking of 3 and 4. Cover crops are highly cost effective because we're assuming that the cover crops are vegetables, and we managed to see in the literature that that is then a profitable exercise by farmers. So the economic costs are actually negative, meaning that farmers get benefits, net benefits from planting cover crops on their land, and that's then followed by buffer strips and nutrient management, meaning the reduction of the application of fertilizer on the land. And wetlands are, economically speaking, the least cost-effective measure, among others because of the high construction costs. This is very quickly about the spatial heterogeneity. So this is the scenario for a 40% reduction, and this is just looking at reducing fertilizer application. So we got these kind of maps for every BMP. This is just for fertilizer application reduction. And then what you see in this map is that the costs vary substantially depending on where you implement this particular measure across the entire watershed. I don't have time to go into much details there, but what I did want to show to you is that we then managed to estimate cost curves relating the amount of phosphorus reduction that goes into Lake Erie, so from the land into Lake Erie based on SWOT, and what the total costs are associated with that. And as expected, the economic costs are higher than the financial program implementation costs, because the farmers do not receive 100% compensation if there is a cost sharing scheme in place, and there is just a small financial incentive payment to these farmers to encourage them to adopt these BMPs. So the total economic costs are, as expected, higher than the financial program costs. We fit the cost curves. It's a nonlinear quadratic cost curve, which is pretty typical in this area. And this is the estimation of the total economic and the total financial program implementation costs based on a 10, 20, 30, 40, and 50% reduction of the loads entering Lake Erie at the mouth near Dunville. And you can see that the difference between the financial and the economic costs increases as the reduction target becomes more strict, if you go from 10, 20 to 40, 50%. Yeah, so if you want to impose this 40% reduction of total phosphorus entering Lake Erie, the costs are around 75 million Canadian dollars per year. And this is the least cost way of achieving that target. Yeah, so we combined the results from SWOT with an economic optimization procedure to identify how we can achieve these targets at the lowest cost possible, choosing from the BMPs that I showed you in the beginning. And then this is a map showing you the Grand River watershed and the 90 subbasins that we identified in SWOT. And then obviously the more phosphorus you want to reduce, the more BMPs you have to implement. So if you go from 10 to a 20% reduction, you see that the number of BMPs increases to 30%, 40%, 50%. Yeah, so if you want to reduce 50% of total phosphorus, this is the number of measures that you have to take, and it also identifies the location where you have to take these measures, taking into account these upstream downstream relationships. So what is the relative contribution of every subbasin to the total discharge of that 386,000 kilograms of phosphorus that on average enters Lake Erie every year? So if we then look at the 40% reduction, take that as an example, we identify what the least cost way is. And so we know where we have to take these measures. And so here on the bottom horizontal axis, you see the 90 subbasins. And then here on the vertical axis, you see the number of BMPs that have to be taken to reach that 40% reduction level based on a financial program implementation costs. And the different colors simply refer to the different types of measures that we use. So you see a lot of blue here, wetlands. Yeah, so light blue is wetlands, dark blue is nutrient management, fertilizer application reductions. So if you just look at the financial implementation costs and you do that optimization exercise, this is the composition of the program of measures to reach a 40% emission reduction. If we then go to the economic cost optimum, you see that there is a change in the number of measures per sub-basin, as I also already showed you in the maps before, but you also see that the colors change. There's much less light blue. The wetlands are less preferred than, for example, there's more orange here, buffer strips. So it allows us to identify how many measures should be and which measures should be implemented where to achieve these targets, in this particular case, 40% at the lowest cost possible. This is another way of representing the two graphs that I just showed you before across the 90 sub-basins. So aggregated across all these 90 sub-basins, what is the number of BMPs, and then distinguishing between the different BMPs. So as I already showed you, we had a lot of light blue, which was wetlands. So under the financial program implementation costs, we have a lot of wetlands, we have a lot of nutrient management measures, whereas under the economic cost, you see much more preference for the buffer strips and for the cover crops. They are more cost effective, economically speaking. And then what we also did was we just checked to what extent do these optimal combination of measures overlap spatially with the BMPs that were implemented as part of the Rural Water Quality Program over the last 20 years in the Grand River watershed. So here you see the number of BMPs over these 20 years implemented under the RWQP. And then if you go for the 40% reduction economic optimization results, you see in blue here how many BMPs would be recommended if you would follow this approach. Yes, so there is overlap, but there is also there are also areas where, for example, the economic optimization, that's the light blue, light green here, advises you to take measures where currently or over the past 20 years, no measures were taken. For example, here at the mouth of the river, there is overlap. So the white areas are the areas where no measures were actually taken, and where also the economic optimization tells you you don't need to take measures there. It's not cost effective. And then there is a yellowish area where measures were taken under the RWQP here in the northern part, a little bit here. But where we, from an economic optimization point of view, argue you shouldn't take measures there. And then the darkish blue-green color is the area where actually measures were implemented and where it also makes sense from a cost effectiveness point of view to take these BMPs. So I'm going to wrap up my conclusions. I showed you that the ranking of preferred BMP measures changes if we start accounting for the costs of these BMPs besides their effects. Economic costs are, as expected, higher than the financial program implementation costs. Also, that has an effect on the ranking of the measures. It's around 75 million Canadian dollars per year to reduce the TP loading from the Grand River watershed into Lake Erie. And that is substantially lower than the estimated 270 million Canadian dollars of damage costs that were estimated a couple of years ago, among others by people from Environment Climate Change Canada. So this is the avoided damage costs. These are the economic damage costs of eutrophication. These costs will be avoided if you take these BMPs, and the costs of BMPs in the Grand River watershed are 74 million per year. So this is a justification for taking these BMPs in the Grand River watershed, but take into account that there are 7 Canadian watersheds draining into Lake Erie, and the Grand River is the largest watershed, but it's just one out of the 7 watersheds in total. So the next steps is to extend the analysis to the other 6 Canadian watersheds, doing the same exercise there as well to scale up the analysis. And we plan to do that under the project called Agricultural Water Futures in the next 2 years. We want to include livestock measures, and we've started discussing the possibility of also incorporating the legacy effects coming out of element from Nandita and Kim. And then when it comes to the refinement of the cost effectiveness analysis, we need more detail on the economic values of cropland. It was very hard to find that information. And as I mentioned, there are different profitability rates related to different types of cover crops. And this is also somewhat of a gap in the literature. So these are some references, and that's the end of my presentation. Thank you very much.
Thank you, Roy, for a very interesting and clear presentation. There's a huge amount of work going in here, that's evident. There is time for a short question or two. If someone has a question.
Can I jump in and ask a quick question? Sorry, Roy, I came in a little bit later. Can you guys hear me okay?
Yes.
Okay, so my question was the 74 million number that you had for the grant. How does that compare to the money that is spent, I guess, annually on the Rural Water Quality Program?
Yeah, so at the beginning I presented some information about the costs of the implementation of the Rural Water Quality Program, and I if I remember correctly, around 97 million Canadian dollars were invested over the last 20 years. Okay. So it is quite an amount of money to achieve that to achieve that 40% a reduction. It's not the same, it's lower than what was invested over the last 20 years, but this would be the total economic cost per year.
Okay, thank you.
I have a question also related to, you said in the end that you're thinking about involving, thinking about legacies in this kind of work, which could be really interesting, I think, to see if how conclusions are robust or if they change. And if you were to speculate a little bit about that, what do you think? I mean, just as one example, I mean, some of these measures are upstream and some are downstream. So perhaps some of them are associated with the cost of, delayed response, where there's others might not be that. So could you just briefly, a few thoughts on that? How could that impact your results?
Yeah, so that's a very, it's a very good question, but it's a very difficult one to answer. I just generally speaking, your costs will not change per year, but the effectiveness will change. So you will only see, as you know, effects over a longer period of time. So the immediate effect will be much lower. And then the cost effectiveness analysis, simply the dollar divided by the kilograms of phosphorus that you reduce. So your, what is it? It's the numerator, right? The top will stay the same. The denominator, the bottom will reduce. So it will become, generally speaking, more costly to reduce these kilograms in the short term. And so it depends very much on how you discount the future and to what extent you're able to account for the future. What will happen to the ranking of the measures based on that dollar value per kilogram of phosphorus that you manage to reduce with a particular measure. And we didn't have the time yet to go into a lot of detail to further specify that. So yeah, I think it's a very important question, but it's a difficult one to answer, to be honest.
Yeah, you need to investigate it, I guess. But what you're saying is that the interest rate, right, could
yeah, because you discount the future. So you can discount both costs, financial costs or monetary costs, but you can also discount physical effects. And so, depending also on the importance that you attach to seeing physical effects now versus seeing them in 10 or and based on the work that Nandita has done, I think there are effects that only show up 20 or 25 or 30 years in time. So if you want to make a decision now, you have to discount the future flow of benefits, so to say, but they're measured in physical effects into that ratio of your costs and the kilograms of phosphorus that you reduce now and in the future. And then depending on the discount rate or the interest rate, as you say, you may value outcomes now more than you do outcomes into the future, and that will have a significant effect on the outcome. And in the sustainability discussion, the argument has always been that you should choose a lower discount rate. The lower the discount rate, the higher you value future impacts.
Yeah. Okay. Thank you. Really interesting. I don't see more hands or comments in the chat, so let's move on to the next presentation. And it's Brian Jacobsen from the University of Copenhagen, and you're going to talk about the Danish approach to P mapping and compare with Canada as well.
Yes.
So, please go ahead.
Yes, thank you. Hope you can hear me. Yeah, so this talk is about basically the Danish setup for the phosphorus regulation. We've not come, I would say, as far as the Canadian, but I thought it was an interesting comparison, both in terms of finding out where the problem is and the time aspect, as well as the measures and the implementation. So I'll try to let's say at the end, I will try to compare a little bit with the Canadian approach and perhaps being a little bit provocative, so that there'll be a lot of discussion afterwards, just ensuring that or discussing whether I got the Canadian approach all wrong. But it was good to have your presentation, Roy, because it gave some insights to some of the stuff that not been too clear in other presentations. But this is mainly about the Danish one, mainly about the phosphorus side and how we have approached it in recent years. So if you just look at the phosphorus thing, you could say that it's been sort of not active in the Danish discussions too much, because the focus has been on the coastal waters and the nitrogen losses. And so phosphorus has been mentioned in relation to lakes and the key challenge with regard to lakes, but it's not been so high on the political agenda. For the streams, the physical quality has been the key issue when you're talking, and this is very much related to implementation of the Water Framework Directive, as Jørgen also was talking about last time. So on the left, you can see a little bit about the quality of the Danish lakes compared to the EU, and as you can see, so roughly around 40% of lakes perhaps might be okay, but quite a number of the share of the lakes in Denmark do need to be improved. Some analysis indicate that the loading, both nitrogen and phosphorus, has diminished over time for selected lakes, but in larger pictures, a lot more needs to be done. As we also saw in the first webinar last time, you could see in a Danish context that both for nitrogen, which is on the left, and the phosphorus on the right, you could see that the point source pollution has been reduced very much over the 80s due to the regulation that was implemented. So the top green one is the wastewater part, the black one is the industry, and then you have the fish farming type thing, and then you have the light blue one, which is this sewage bypass. It's this water that's not going through a proper cleaning process, and the last one is sort of more rural housing type. So you can see that there's been a clear reduction from the 1990 to, let's say, around 2002, 2005. And after that, it's been more difficult to actually obtain a reduction when you're talking the point source. I think it's fair to say that the point source is very limited compared to the diffuse pollution when you're talking nitrogen. But when you're talking the phosphorus part, it's a larger part as such. So, but if we go to the agricultural part, how has the surplus and so on developed over time? The top left one shows a little bit on the phosphorus surplus in tons of phosphorus over the last 100 years, and you can see that there's been there was a drop during the Second World War, and then there's been an increase until 1980, and then a decline after that. So we are, as the graph will also show further on, we have a little bit of surplus left, but it's limited compared to what it used to be. If you look at the bottom left, you can see the surplus divided into the different types of inputs and outputs. So the dark blue one at the bottom is mineral fertilizer, and then you have the green one, which is livestock manure, and they give just about all of the phosphorus applied. Then you have the harvested part, which is the yellow one, and I think over time you can see that there's been a tendency to a larger harvest in terms of the phosphorus, but you can also see that the application has been reduced somewhat, at least over time. So we have, if you look at the red line, you can see the actual phosphorus surplus, and you can see that's been limited in a number of years, but has in recent years increased a little bit. There's different discussions on why this is. Some say it's the feeding, and others arguments been discussed. And also I should point out 2018 was a drought year, so in that sense the very low harvest, it gives a very high surplus. If you look at the right-hand figure, then you can see that there's been an accumulated phosphorus loading, and this is something that which farmers might not see this, but it's sort of attracting attention when you're looking at the losses. So this also has to be in the picture when we're looking at the phosphorus losses, as it might be potentially lost over time, even though phosphorus is quite good at retaining the application. And this is just to show the actual mineral fertilizer sales in Denmark. So you can see for the green one, you can see the nitrogen one actually have a quite clear reduction, but in the last 10 years, it's been difficult to reduce that one even more. With the phosphorus, the mineral fertilizer has been limited now in a number of years, and it's quite uneven purchase, but I come back to that a little bit later. So in a Danish context, farmers are often focusing on what we would call the P number, or the phosphorus number, which is calculated and coming out of soil tests. So a lot of farmers will be focusing on whether that phosphorus number is too high. So when they look at whether they are, let's say, responsible for any pollution, perhaps you could see here on the top left graph that if you got a figure around 6, then from there on the losses could occur. So as long as you're under 6, then you're sort of okay, and so you think there's a binding capacity of the phosphorus there. On the right-hand side, you see a curve of the actual phosphorus numbers in a Danish context, and you can see the highest numbers, that means that just about over 5, is to be found in the western part of Jutland. This is also where you have the livestock, so it's not a surprise that this is the case. And you have the lowest phosphorus number on the east, on Zealand, also where Copenhagen is situated here, and that's where you have the arable farming mainly. So from a farmer perspective, what has been told over a number of years is that if you have the phosphorus number, you could say below 2, then you can apply more phosphorus than the actual crop would need directly. If you're in the range of 2 to 4, you just apply the phosphorus that the crop is needing. And if you are over 4, then you should only apply less. You simply apply less than the crop is taken away. So in that sense, you have some clear guidelines for this. And then in that sense, farmers would say, well, I'm following this and I'm trying to keep my phosphorus numbers down. And as you can see on the right here, you can see that the phosphorus numbers, the yellow ones, the orange bars here, have gone down a little bit over time, even though there are a number of areas with P numbers that are sort of similar, not similar, they're quite high, I would say over 4. So there's still areas with some issues when you look at the phosphorus numbers, but the overall perspective is a slight reduction. So now we move into the present time, and that is a more detailed phosphorus risk analysis provided by Hans Estrup, which is also listening in. So every mistake I will make, he can join. He's welcome to join in and adjust what I'm saying, because it might not be completely correct, all of it. But this is some of the different loss passes that their analysis have shown. So on the top left, you have water erosion. On the right-hand side, you've got matrix losses. You've got the macropore phosphorus losses, and you've got phosphorus losses here from the organic low-lying areas. And you have finally here and the losses from the embankment next to the streams. So you have a lot of more loss passes than just looking at the phosphorus numbers that we did before. So in that sense, the whole concept is a lot more complex now, and also the mapping of this has been extremely difficult. It has been going on for, I think it's fair to say, quite some time. But last year, the report came on this, and it's interesting reading, because it sort of shows that the areas are, you can actually map the areas where you have the loss potential for these different types of losses. And so in that sense, you can also see that the map is not just a clearly, let's say, livestock related or whatever. So these are the different areas. You can see the dark red or orange areas where the losses are quite high, but you can also see some blue areas where the losses are quite low. So this is what are going to be used in the analysis that we are doing to perform this year on this issue. So if we just look at the overall picture for the losses, I have done here on the left-hand side, you can see the different types of losses. And if you look at the right-hand one, you can see one where the share has been divided without the bank erosion losses, and also one where it's included. I think what you can see is that the macropore loss and the low-lying areas, they constitute quite a large part of the total losses. And you can also see that the losses from the embankments is quite a substantial part of the losses. So in that sense, when you're looking, the fact that the erosion is let's say in the range of 50% of the total losses, it is some of the key areas that we need to look at. And I think that's not been so clear until now in a Danish context. So again, just to compare, so if you look at the left-hand side, you can see the phosphorus balance overview. And it's clear that you've got the surplus on the left-hand side again. Jutland got the yellow and the green areas where you have a surplus of 5 to 15 kilograms of phosphorus per hectare. But you also got the interesting thing here that Zealand actually got a minus. So the application of phosphorus is actually lower than what is taken away with the crops. But the link to the risk map that we saw before is not like 100%. So you can see that it's not straightforward comparison. And so I probably, as Hans would agree, that phosphorus is a complicated issue. And I thought nitrogen was very complicated, but phosphorus could perhaps be even more complicated to deal with. Some of the Danish discussions have been, how come farmers in the West here buying mineral fertilizer? And one argument is that they buy mineral fertilizer, phosphorus, to apply in maize crops, early maize crops. Because if you look at Jutland and the island here on its own, it actually is self-sufficient in terms of phosphorus. So you could almost say that they could just rely on the manure and reallocate it better. But this is not the case. There's quite a number of buying mineral fertilizer. So if we look just at the regulation right now, what is it farmers are looking at? Well, there's been a limit on the application of phosphorus that was introduced here in 2016-17, and basically that level of let's see if I can just show you again. So basically this level that was introduced in 2017 was basically the same as the nitrogen regulation implicit gave, okay? So you had a limit on the application of nitrogen from livestock manure, and with that phosphorus that was following, you could say the nitrogen, you were given levels of phosphorus like this. So the only sort of real reduction was the poultry and the mink farms, where they had to reduce their applications quite significantly, whereas the rest of the farmers were almost applying the same, just sort of in rough terms. Then you notice that is this tightening, and that is because certain lakes, vulnerable lakes, they were pointed out. So 25% of the area were considered being near a catchment of a lake. And so they had reduced targets here, reduced application rates. And so this is moving on to 2020. You can see just about the same rates. And what we are standing in the middle of now is that there will be a discussion on these limits and the levels in 2021 here, and also for the coming year. We don't know where that is going to be situated, but as you perhaps can see, is that the application 30 to 35, and then removal of about 25 to 30, it still allows somewhat a surplus in certain areas, although less than before. Yeah. So the work that we do in a Danish context is that we use these catalogs where we make a lot of measures and try to calculate both how they are implemented, how the efficiency, as Roy was saying before, as well as the cost of this, and trying to use this, and trying to have, let's say, a national consensus on these measures, so that when the politicians are using them, they can actually rely on what's in there. So the nitrogen catalog is the third or the fourth one that we had done, and I would say the phosphorus one here at the bottom is just about the first larger one that's been done. And so in that sense, it's be interesting to see how all this is going to be used in the future planning. This is the measures, and now we're coming back to what Roy said about the efficiency as well as the costs. So if you look at this this column, you have the efficiency, and here we have a division because we have areas where we know there's a high risk, we have medium risk, and we also have low risk areas. So this is just the high risk areas, and so in that sense we have already targeted, let's say, this. So you both the fact that you have the measure, but you also have the measure targeted a certain area where the losses. We have, for instance, the negative phosphorus balance. And as you saw Roy before saying about a cost of negative phosphorus, we also have a cost, but that cost is related more to the fact that the farmers have to drive further with the manure than otherwise. It's not a loss in terms of yield. You can see that the eastern part of Denmark have lower applications for a number of years without actually having lower yields. So this is some of the bits and pieces that are interesting to compare, how the measures are implemented across countries, but also the efficiency as well as the costs across countries. You can also see that we have the buffer strips, for instance. They are similar, a little bit more complicated buffer strips than the normal one, but we would say that it's not likely to have that farmers would do vegetable cropping in the riparian zones. We would say that's a specialist issue. So we would say they would only have grass, and so it'll come with a cost, but also a limited cost. And also we also have the wetlands. We also have mini wetlands in there and other measures. And we have reduced tillage, newer things in the Danish context, but catching on, and is perceived as having negative cost. In other words, it's a profit for the farmer to apply this. And this overview, I try to do it both in terms of Danish kroner as well as Canadian dollars, just to compare, because we're trying to write up so we can compare some of these measures between Denmark and Canada. Yeah. If you look at also the future in terms of the implementation and analysis, we are for the lakes. Henriette was also might be listening in on this, is our key project leader for trying to find some measures for the phosphorus part. We're doing 2 different models have been used in trying to find which measures to be used for each lake. And so we have a number of lakes that have been identified. And so for each lake, you will see both of how much phosphorus loading is there now and what is the target phosphorus loading. And so you have a reduction requirement for each lake. This is mini lakes compared to Lake Erie, so I wouldn't, it's almost not a lake, you would say, but it's just in the Danish context, we need to try to set up some measures and try for each of those lakes just to get an idea of how to get further in terms of reductions. And on the right-hand side, you can see this, the ceiling of the application limits, and they will be probably reduced in certain ways in the coming years, but we'll see how much and how that is going to happen. So this is very much about the regulation in Danish context. And just to finish off with the controversial comparison, I would say that if you look at I'll be looking into mainly Lake Erie more than the Grand area, but I would say the pressure for having a change is higher in a Canadian context than in a Danish context. And it's been for a number of years, quite a number of references talk about a 40-year, let's say, focus on trying to reduce the phosphorus losses. That's very much on a local government type thing in a Canadian, as the way I see it, whereas in a Danish context it's national government otherwise, but also the countries are quite different in size. And I would say one thing that I have noticed is that there's not so much detailed planning, analysis and so forth in the Canadian side. So it's surprising perhaps to me that in an area and an issue which has been a key focus area for 40 years, that the analysis type, the one that Roy just presented, has been very limited, or I would almost say non-existent. If I was trying to find the cost of implementing measures in Lake Erie, I would just about not find any. And also, if I was trying to say how much will it cost to get a 40% reduction, I couldn't find any numbers. Roy's numbers is about the first number I've ever seen in that thing. Also, in terms of the mapping, I find that the mapping has been limited. I might be too hard on this. I'm not a phosphorus expert, but I would say that some of the mapping that we are trying to do in a Danish context could help, also perhaps in a Canadian context. Then we have all the issue about actual implementation, and it's clearly two different ways. The Canadian one being a lot more voluntary approaches, the 4 Rs. So the issue, as I can hear it, is very much about approaching selected farmers and hope they are positive towards this and they will be positive towards the whole approach. And so a lot less on limits and targets set from a, let's say, government perspective. But I also think the whole culture is different. So I think Canadian farmers are not used to any national, let's say, government regulation type thing. So they would probably run away crying, or shouting or whatever, if that was the case. Whereas in a Danish context, we are a lot more used to have this because farmers already have had the nitrogen accounting for many years, and so just using that for phosphorus accounting is let's say possible. And also in that sense, you could also say that the control part is perhaps more strict in a Danish context. But it also means that it has been more difficult to actually see improvements over time in a Canadian context. And I think it's one of the challenges, and is that even though you do something, if you have, let's say, a legacy issue compared to a climate issue, then even though you've done something which is good and is meant to do the right thing, then you will actually not see much improvement over time. And so farmers would say, oh, I did a lot of stuff, I can't see anything. Why did it, what's the purpose? And finally, I was reading about certain, let's say, very few cases where the reservoirs and also some heavy rainfall was a key contributor to this. And I think that's also some of the issues that need to be, let's say, analyzed more. It's very difficult, but these sort of storm events, how much do they contribute to this? So might being a little bit unfair, but I think actually both countries could learn a little bit from each other in terms of this, in terms of how it could be done, but also when to expect improvements over time. So I'll finish just with the conclusion, saying that we've just started on the phosphorus side. So we are not the ones knowing exactly how to do it. We have a certain path based also our history in terms of regulation. The Canadian approach has been a long more coming, but the results could have been, let's say, better. It's a complex issue to deal with phosphorus, and also in terms of linking it. So this old history about just linking it to livestock intensity or just linking it to phosphorus surplus is perhaps limited in certain ways, in certain cases. Then about the implementation, I think perhaps I would think that the Canadian approach with the soft approach, if you want improvements, perhaps need to be a little bit tougher and a little bit more straight to the point. But I can also see in a Danish context that farmers think it's complex enough to deal with nitrogen. Do I need to do something specific for the phosphorus on top? It'll be all too complicated. But I think also in terms of the mapping, I was saying that if you get down to the mapping and actually get some really high focus areas where you have a high loss, then that would be good to be able to pinpoint them if possible. And then just to finish off in terms of the legacy issue, of course, with this project, is that trying to compare, or trying to actually, I would say perhaps to the politicians to say to them, when are you expecting an improvement? So that they don't expect the improvement tomorrow when it comes in 20 or 25 years time, when, as Nadita was talking about last time. But it's not an easy, and as Søren will come into in the next one about the benefits also, but this legacy thing, we have to be able to at least sort of indicate it a little bit so that the politicians know when to expect improvements. So thank you. That was what I had presented in mind to present.
Thanks a lot, Brian. Very interesting presentation with the Danish perspective, where you seem to have some, momentum in the changes. Nice with the international comparison also. And there is time for short comment or question if someone has. Don't see anything right now.
I want to make one comment, Jörg, if I can.
Yes, sure.
So, because it looks to me that one of the differences I noticed that in Brian's analysis, it shows also that looking at negative phosphorus losses is one of the basically what we would call a BMP. And to a certain extent, that's already starting addressing the legacy issue. Because if you have a negative phosphorus loss, then essentially you would also expect a reduction in the legacy. So maybe that's a way forward also in on the Ontario side, is to start thinking about, and of course, using SWOT might not work very well here, but with some of the models that Kim and Anita have been developed, that could be done. So to really explicitly then account in the analysis, whether it's a economic analysis or just a biophysical analysis, is to say, well, let's also count that as a BMP. If you can show that essentially you're starting to have a negative phosphorus loss, which essentially means that you're no longer building up a legacy, actually reducing your legacy. So maybe that's one way to go forward and to use this analysis that you just presented.
Yeah. Roy?
Thanks, Brian. I was wondering if you would be able to comment very briefly, perhaps, on the role that the Water Framework Directive also played in how you approach this issue in Denmark. So the comparisons between Denmark and Canada, but Denmark is part of the European Union, and they have this piece of legislation called the Water Framework Directive. Can you maybe comment maybe a little bit more on how instrumental that has perhaps also been in moving policy forwards in Denmark when it comes to these nutrients management issues?
Yeah, I mean, I think it is a key issue. I mean, we are dealing now with the third planning period, and then trying to get the very best, and so in that sense, you could say, I would say, especially just setting up the starting point was one key issue for the starting at the beginning 2015. So I think it has moved along, but it also made it like that the countries have to implement something. It's difficult to come for the third planning period and say, oh, we have done nothing for phosphorus in relation to lakes, as Jörg was saying a little bit last time. It's difficult to keep on saying, oh, we haven't done anything, or we haven't got any data, or whatever. I mean, after 12 years, you should have some data or something. But on the other hand, you could argue that what you have as the planning, which is a combined between the US and Canada, is a similar, let's say, issue where you actually also say to each other, we want a 40% reduction, but I perhaps feel that there's less let's say, power in that organization. Although they're quite critical, as I was reading, quite critical in their analysis, they still have less power in actually terms of political implementation than the Water Framework Directive have, because they come with a whip. I think in this third planning period, if the countries are, well, they do already, but they will even more so come with a whip and start chasing people around.
Thank you for that response, and thank you, Brian.
Can I just ask Jørgen, just quickly,
Yeah, sure. Just quickly.
if Hans, if you're here and you are willing to say something, you're very welcome to just say a few things, Hans, because you're the expert, Danish expert on this. So I'll just taking some of your stuff.
I think you did it very well. Just one comment regarding this accumulation of phosphorus in the soil, the legacy. It's part of the story, of course, but the transport pathways are actually just as important. You can store a lot of phosphorus in the soil and it will just stay there for centuries if you don't have a transport pathway. So addressing the transport pathways with measures is very important.
Thank you. And I made it.
You did, Brian, very well. Thank you. So it's time to move on to the next presenter, which is Serene Wilson from the University of Copenhagen. And you will talk about the choice experiment from 4 different countries. Please go ahead.
Thank you, Jakob. So I will sort of move from the cost side onto the benefit side of things. Just a second. There. So I'm going to be presenting basically results from the choice experiment study we did as part of this LEAP project, focusing on the time lags, the legacy issue, if you will, and then also the outcome uncertainty related to making these different steps towards improving water qualities, focusing on what are the values. So here are the 4 different case areas we've been working in the 4 different participating countries. A bit of facts about that, and really the interesting stuff here is that water quality needs to be improved in all 4 case areas. Green color here indicates sort of good ecological status or similar. So there's definitely room for some improvement, and as we have just seen, this will be a costly procedure to reach good ecological status, or at least to improve significantly on these water bodies. It's reasonable to also consider, well, one thing is the cost efficiency, obtaining this in the least cost way, but also whether are the benefits actually outweighing the costs? Is this something that is a good idea for society? Well, that's sort of the purpose here, to try to bring about some estimates that can be compared to the costs, to basically make that cost-benefit sort of cost-benefit justification for actually spending the money. Or for those of us in the EU, there might be the opposite argument, that it's disproportionately costly, in which case it might be possible to get an exemption from the Water Framework Directive. So we've set up this choice experiment survey, realizing that we're interested in assessing these water quality improvements. The benefits of them are mainly non-marketed, recreational values, or the slightly more challenging non-use values such as existence or bequest values, for instance, related to biodiversity. When we have such values, we need to resort to these stated preference techniques, and that's why we ended up doing a choice experiment survey. Another reason was that we wanted to focus on different issues. So one thing was, of course, the preferences for water quality improvements as such, measuring those in monetary terms. That has already been done quite a number of times. Lots of studies are around. What we found was that there were very few studies, if any, that specifically addressed this effect of the legacy, the effect of time lags on the value estimation. And another issue which has been addressed in a few instances in the literature addresses the outcome uncertainty. This was something we wanted to also bring in here because we sort of realized that it relates quite closely to the time lags. So doing a choice experiment is something involving a questionnaire survey. So we developed a questionnaire. Here's a description of the questionnaire development phase, and this is the point where I should definitely acknowledge all the partners in the LEAP project for helping out with this. Basically, we spent a lot of effort making sure that the questionnaire would work as we wanted it to, measuring people's preferences for these different aspects. Water quality was the sort of the main component, so we needed to describe water quality changes, and this is a notoriously tricky thing when you do these kinds of studies, because while hydrologists might know exactly what a change in water quality implies, most people will have little knowledge of the natural science components, so we had to describe it in sort of easily understandable terms and keep it as simple as we could. So here is the description. This is specifically for the Canadian case, 3 different levels of water quality: poor, moderate, or good. And you can see how different aspects that we would believe and that we confirmed through our questionnaire development phase, different aspects that might be important for the values that people get from water quality. The Portuguese case was slightly different from the others, because here the focus on water quality was more on the physical conditions than the biochemistry. So here we used slightly different descriptions, again, to basically end up with these 3 categories: good, moderate, or poor water quality. So that also means that it's, while I will present some results on these preferences for water quality levels, they are, strictly speaking, not directly comparable across the 4 countries. And this is one of the reasons. So here's some more details on how we described this to people, how we described our scenario, because when you do this, you have to describe some kind of scenario. So our sort of a basic approach here was to, and this is just taking the description for the Danish case, Limfjorden. It's very similar for the other 3 areas. Basically saying that, well, we expect the water quality to change if we don't do something, if we don't adopt a new policy. We expect the water quality in basically the entire Limfjorden to be classified as poor within the next 4 years. And then basically what we're then, and I'll show that in a second, what we're doing is we're then showing people the possibility, or giving people the possibility to show their preferences for increasing that water quality level from poor to moderate, or from poor to good. We also implemented here a characteristic about the risk, because we wanted to address this notion that even though we have all these measures, Brian and Roy just presented a whole bunch of measures, sometimes for various reasons they just don't work, or they are much less effective than we expect them to be. So we wanted to implement that to see how people reacted to that, because very often in these surveys we present these water quality improvements as something that will happen for sure. And if anything, I guess what we have seen, at least here in Denmark, in the last years, is that these water quality improvements don't just happen. They seem to be difficult to bring about. And then at the bottom here, you can see our time lag characteristic, our legacy aspect. We defined in the status quo situation that it would take about 4 years to reach the poor ecological status in case we don't implement any policy. And here we then essentially varied that range of years from 4 to 8 years, or 4 to 20 years, which would then be the time range within which these changes could occur. We also had a price in here. That's one of the things you need to include in order to be able to extract preferences in monetary terms, what we call willingness to pay, how much people are actually willing to pay to improve the water quality or to reduce the risk of not improving the water quality, or to bring those water quality benefits forward in time. So here we included a tax payment, simply saying to people, well, you know, you will get these alternative policies you can choose. They will, to some extent, improve the water quality, but you will also have to pay a higher annual tax. So that was implemented to make sure that people make these trade-offs between environmental quality and money, basically. So here's an example of the choice situation that is essentially where we elicit people's preferences. So this is for the Canadian case. And as you can see, we had sort of the current policy as one alternative, and then we presented two different policy proposals where water quality would to some extent improve in parts of the Grand River in this case. And then there would be varying levels of risk of this improvement not occurring, and also the number of years before this improvement would occur also varied across the alternatives. And then there were varying prices or tax increases that you would have to pay if, for instance, policy proposal 1 was implemented. You would actually have to pay $15 extra in taxes per year. And then basically people make a choice. Here the respondent in our questionnaire has chosen proposal 2. And well, once we have that information, we ask another choice task or choice situation. So here's the next one. We ask the respondent to choose here again. And we do that 12 times. Every time it's a different situation. So we basically extract a lot of information about how people make these trade-offs between the different characteristics here. And that's how we can elicit the willingness to pay. So here, some info about the data collection. It was an online survey in pre-recruited web panels, about 800 respondents in each case area, and we did some cleaning of the data. I'll skip that. One thing that was slightly disappointing was that we ideally aimed to have representative samples. So we sample 800 respondents from these 4 areas, hoping that they would represent the target population. So basically the entire population in these areas. When we compare the demographics, the social demographics between our samples and the populations, this is just for the Danish case, but it's more or less the same picture from the other case areas. We see that we have in our samples an overrepresentation of people with long educations and high incomes. And in some cases, the gender distribution is also a bit off, and also the age distribution. So that is something to remember when interpreting these results, that we might not have a totally representative picture here. So results. So here's the Canadian case, and what you might notice first of all is that at the top we have the different preferences in terms of willingness to pay estimates for obtaining good ecological status or good water quality relative to the baseline, which was the poor, at least for the lower Grand, it was a poor water quality. For the upper Grand, the baseline was a moderate water quality. So I'm not going to go much into those estimates, those willingness to pay to improve water quality. That's something that has been done before. And basically the numbers here, the magnitudes of these willingness to pays are quite similar to previous studies, previous similar studies. But really what's interesting is to see the effect of these risks of not making the improvement as expected. The Canadian case is slightly particular here in that we would expect people to have a negative, you could say, a negative preferences for increasing the risk. The higher the risk of not obtaining the expected water quality, of course, we would expect the willingness to pay overall to be lower. And we do see that for a 40% risk reduction, or sorry, a 40% risk compared to no risk, people generally require a compensation, or they have a reduction of their willingness to pay of about 80 euros per household per year. It's a slightly strange result, the 17 positive. It seems that people have positive preferences for increasing the risk from no risk to 10% risk of not making the expected improvement. But yeah, we don't have any good explanations for that, but it's there. What you might also see, and this is where the legacy issue comes into the picture, the time lags. Compared to obtaining the improvements in 4 years' time, if instead it takes 8 years, then the willingness to pay reduces by 21 euros. And if relative to the 4 years, it instead takes 20 years before we actually see the improvement, then there's a reduction in the willingness to pay of 38 euros. So this conforms sort of to our expectation that the further into the future we get the benefits, the lower the value they have for us today. Here's the Danish case. I'm just going to very briefly highlight. We have similar results, not the same issue with the low risk here in Denmark. Here it looks as expected. Here's the Swedish case. Here the risk looks as expected, but then there's a strange result here for the going from 4 to 8 years is apparently positive to the Swedes. We don't have any good explanations, but there is a lot of heterogeneity built into these models here, and this is something I don't have time to go into, but this could be one explanation for this. And here's the Portuguese case, again conforming more or less to our expectations. The higher the risk, the higher the reduction in willingness to pay, and the longer the time lag. Well, in this case, the -30 and -24 is more or less the same. No significant difference there, but somewhat surprising that we don't see sort of a further reduction in willingness to pay when moving to 20 years. So based on this, we can calculate the implied discount rates, and this is what Roy talked about half an hour ago. The lower the discount rate, the higher you value future impacts, and that is exactly what we're working with here, trying to assess the importance of when do these benefits actually occur, how important is it for people, how much do they discount these values when they occur further into the future. So here we have calculated these so-called discount rates, and I'm not going to go into what the underlying theory, but just to note that here we have the officially recommended discount rates for the 4 different countries. And what is interesting to note here is that in all cases, the official recommendation is higher than what we actually find when we ask people directly. So this could be, well, at least an interesting finding in the sense that it might actually lead to underestimating the benefits of water quality improvements in the long perspective in standard economic analysis. So we find that people have strong preferences for water quality improvements. That's not surprising. We find that the time lags matter as we expected. We generally, with some odd results here and there, but generally we find, as expected, that people discount the value of water quality improvements when they occur further in the future. But it's really interesting to see that those discount rates are actually relatively low. And as I said, this could have implications for how we normally conduct economic assessments of water quality improvement policies. And outcome uncertainty also matters. The higher the uncertainty, the lower the willingness to pay. And an interesting finding here is, or at least something to note, is that when we introduce even a 40% risk that this expected water quality improvement is not going to happen, still people actually have a positive willingness to pay. So just the chance that water quality will improve is actually something that people still value. So there could be an argument for also using some of those measures, which we might not be fully confident about whether they work or not. But of course, in the end, that might put us in a situation where we haven't actually increased the water quality. But at least at the point of time where people can say, well, if we're talking about something in the future, it actually has value to me that there is a chance that the water quality will improve. So overall conclusion here is that it's important to account for these aspects in cost-benefit analysis, the type of analysis, economic analysis we often do when assessing policies. And this represents at least one attempt to do so. And I think I will, in the interest of time, I'll stop it there. I'm sure you agree, Jakob. So thank you very much.
Thank you. Thanks a lot for this presentation. And I think you have actually lots of unique, interesting results here with this large study in many different countries. And it seems like some results are consistent among countries as well. So it's really interesting. So let's see if there are some questions. We have time.
So when there's a risk of obviously water quality improvements not happening, you think the reaction, people's reaction is that it's essentially they're still willing to pay because things could go worse. Because in your choices, you had only things are not going to improve or they're going to improve. Maybe part is that, hey, maybe if we don't invest, true. In this case,
yeah, I mean that could potentially be part of people's reason for exhibiting this positive willingness to pay. We can't really we can't make that conclusion. We can't. I mean, at the outset, basically what we have described is that the water quality will stay where it is in case this improvement doesn't occur. And of course, in reality, it would be somewhere in between, right? But from sort of I mean, yes, there's in our worst case, there's a 40% risk that you don't get the improvement. There is still a 60% chance that you do get the improvement. And basic theory, economic theory would also suggest that people should still then overall have a positive willingness to pay for that. Yeah.
Okay, yeah, thanks. Roy?
Yes, sorry. Yes, I had a little bit of a similar question because of the difference between willingness to pay to improve the situation versus the willingness to pay to accept a potential deterioration. I think you already answered that question. I just wanted to share with you that the results that you find for the grant are they're a little bit on the high side, but they're not very far off some of the values that we found in a meta-analysis of water quality evaluation studies across Canada. So we ranked that based on the water quality ladder of fishable, swimmable, drinkable, and if I remember correctly, we didn't get higher than 200 Canadian dollars per household per year. And I very quickly did a conversion from the euros to the Canadian dollars. And I think what you found for the Grand River Watershed was around 240 Canadian dollars. So that was per household per year as well. Is that right?
Yes. Yeah.
Okay.
Yeah.
So it's a bit higher than what we've. Yeah. It was per household. Yeah, so it's not very far off. So we got around $200 per household per year for the highest level of drinking, for water quality improvement, which was drinkable. And so the values are a little bit higher than that, but they're not very far off what Canadians more generally are willing to pay for water quality improvements across Canada, which is good news.
Yeah. Good. Brian.
Yeah, I think my question was mainly that now we're talking talking about the discount rates. Then often when we do the analysis, we actually don't include them at all in terms of the physical ones. So we just assume that you get the water quality like tomorrow, and perhaps some of these analysis here sort of allow us to actually say, in case we say it'll come in 20 years and it'll be a discount of either 2 or 4% or whatever, then that's the cost we're talking about in cost efficiency. Then the next question could also be, to what extent does that change the ranking? Because I'm not strong enough to to deal with some of those, but you could actually say that some of these measures could be pushed forward if they had, let's say, an immediate effect. So that measures that have an effect tomorrow compared to the measures that are having an effect in 20 years could then be differentiated. But I don't think in the Danish context we're there. I'm not sure you're there in the Canadian perspective, but that will also be an issue.
Okay. Yeah. So are there any final comments or questions? Actually, I have like a short, we're running out of time soon, but I have a short, more like technical question. You said, of course, it's difficult to get representative, group of people, and you made efforts there. But there are some, more educated people answer to greater degree and so on. Could you see trends in the data set? I mean, is there a chance that one could correct these potential biases with the data set itself somehow? So, or how to, what's your comment on that?
Yeah, we haven't done that, but that is a possibility, because one of the things we would typically expect from theory is that those who have a higher income also tend to have a higher willingness to pay. So it's kind of obvious that if we have an overrepresentation of those with the high income, then we are essentially also overestimating the willingness to pay in the broader population. And there are ways to adjust for that. We haven't had time to go into that, but it's definitely possible with the data at hand.
Yeah, that sounds great. Okay, then I would like to take the opportunity also to remind that there is a third and final seminar this Friday within this LEAP series. So if there are questions remaining, and you're most welcome to join this seminar. It's on legacy challenges regarding nutrients around the world. And with this, I would like, unless there is someone who has a really final comment, I would like to thank you all for participating with all these questions. And in particular, of course, thank you to the 3 speakers, very interesting talks. And I think it brings together what we did in the LEAP project very well with all these different aspects. And see you in the next seminar. Thank you.
Thank you.
Thank you, Jericho.
Bye.